Second years, welcome to Parametrics. We have done so much today. You should be so proud of yourselves, second years, because the first years, whilst I think it is absolutely amazing that they're, stepping up to the responsibility of learning it themselves, they could easily, the first years could easily think, my teacher will sort it in September. Now, their teacher probably won't be able to sort it in September because there's just simply not enough hours in the day, but I can see that that would be a tempting way to think. You guys, it would be so easy for you to just put your feet up now and say, I'm just going to see what happens. By the way, I'm pretty sure I know how your grades are going to be awarded now, but I cannot tell you, I'm afraid. So we're on it. We have our inside sources. Just make sure that you have hit subscribe on the Tailored Tutors YouTube channel. The second that we're allowed to talk to you about it, then we will. I think that it's like if they're doing what we think they're doing, what we've been, the rumors around the people who know, then I think it's really good idea. Okay, I do honestly think it's a really good idea. I think that obviously there are still going to be people who get grades that they're not happy with, and we do need to prepare for that, which is the whole point of the exambulance, is to keep this ticking over an hour a day, just so that if and when you get your grade and if you don't like it, then we are ready for you to stick two fingers up to the system, go into that exam in September or whenever it is, and smash it, completely smash it. So that's going to continue to be what we're working towards. But make sure that you've hit subscribe so that the second that we do find out that we can talk to you about it, then we absolutely will, and answer all your questions and concerns and that kind of thing. Right. Timer, 45 minutes. Action hour rule number 1. Action hour rule number 2 is that we have a clear focus. Now, the clear focus for today is parametric equations. But I also, before we start, want to point out to you how amazing you've been this week and what we've done in 1 week of 1 hour a day. The first day, we covered this entire thing, okay? All of it. We talked through all of it and what was in it and what we needed to work on, and you said what you needed to work on and that kind of thing. Since then, we have worked on all of the differentiation, and if you've used your playlist wisely, then you now have a complete set of notes on differentiation. We've also spent a lot of time on integration, and the only integration thing we haven't done is solving differential equations, which we'll come back. It's not really a big topic, it's just integration. Next week, have a look at the schedule in the exambulance. It says what we're doing, okay? What else have we done? First is this morning, I worked on all of this vector stuff in the last hour. So and I have made this, I haven't, but I will make that previewable at the end of this session. So if you want to look at the vectors stuff, then that's going to be available over the weekend as well, because we've now got 2 days. Today, we are looking at parametrics. Now, parametrics kind of comes in with functions. So we've got parametrics and converting from parametric to Cartesian, which is number 9 and number 10 of the A level. We've also got parametric differentiation, which we did already talk about because it's the chain rule. And we've got parametric integration, which actually we did already talk about because it's integration by substitution. So it spreads across these 3 areas: functions, differentiation, integration. And to be honest, it also, this is year 13. Let me just change it. I had to change it while we were going because of boring reasons that you don't need to know about. I will now change it to year 13. Yeah, year 13 we are on now. Sorry, I've changed it back. So, it spreads across all of them. And to be honest, there's also some trigonometry in it. Now, the only trigonometry you really need is the Pythagorean identities, but you might also need the doubly halfy ones as well. And these are the things that all come together to make parametrics. Converting them, differentiating them, integrating them, and converting them involves the trig, and differentiating involves the trig, and integrating involves the trig. So that's how it all fits together. That's its place. So the trig might feed in there, the trig might feed in there, and the trig might feed in there. Okay, right. We're not starting with parametrics though, we're starting with integration. Integration is the most important thing in the second year, and in fact in the A level. The reason it's so important is it's worth a lot of marks and it takes a long time to get good at it. It comes together, but it comes together slowly. I'm going to remind you of my rules for integrating. Rule number 1 is that there's no such thing as integrating. So your thinking must always be in this direction. Differentiate. Never try to integrate. Try not to think of integration as being a process. It's always writing down what you think was differentiated. There are only 10 answers. If the question is what was differentiated, there are only 10 answers. It's either cos, sine, sec squared, cosec squared, sec, tan, cosec, cot, e to the a to the 1 over or x to a power. That's it. There are no other functions. It's one of these 10. Some of the things that we get, they can't just be looked at and the answer written down. So the 10 are the ones that we can just look at and write the answer down. Now, there are ones that you can't just look at and write the answer down. And that's what led us on to looking at fractions and what we would do with fractions, looking at some trig things, like particularly trig squared. What do we do with those guys? Because that's not any of the 10. And places where a substitution would help, the method of substitution would help, and times when parts would help. And we looked at the fact that there's only 3 times that parts would help. And those 3 times are stuff to do with x, e to the stuff to do with x, stuff to do with x, trig function to do with x, and learn. That's the only time you need parts. Okay. So what we did is we looked at different techniques that turn these things from things we can't do to things we can do. But everything on this page is pretty straightforward. I'm going to give you, oh, I didn't press start. I'll press start and then I'll give you the first, I think, now 3 of these you can just write down the answer. So they take 30 seconds each, 15 seconds each. And then the other one you might have to do a little tiny bit of work. So I think 3 minutes is going to be totally fine. Okay, that was 1.5 minutes. I'm going to do 2 things. Sorry, I missed something really quite important of number 3. So I'm going to put it back on, which is that, is what I meant to do. We can discuss at the end why that little squaredy guy there is so important. Basically, that I've now made it go from impossible to really easy. And I'm going to give you a little step for this one as well. You've got another minute or so left. I think to create room, okay, it's been 3 minutes. I'm going to have to get rid of all of that because I can't delete. So, right, so let's have a look at these. The first one is an example of this guy. So what I can see there, just by looking at it, what I can see is that I've got a trig function, and that trig function is applied to some complicated thing, in this case, x squared, right? But that thing, x squared, I can see the derivative of it. I can see the u prime. I can see that the derivative of x squared is 2x, right? Now, okay, fine, that's 3x, but I can fiddle that. That's absolutely fine. It means I know immediately what got differentiated. What got differentiated was tan. Done. No work needed. Now, you can only do it like this if you're really good at using the chain rule without using that u equals. If you do the chain rule by writing out u equals and then doing du, dy by du by dt, whatever it is, then this is going to be difficult because I'm looking at it and seeing the chain rule, which you can only do if you use the chain rule without doing that additional work. Now, have a look at that tan x squared. What happens when I differentiate it? I get sec squared to x squared, brilliant. Then I multiply it by 2x, great. I don't want the 2, I do want a 3 at the end. Next one, what got differentiated? It must have been this, because the derivative of e is e. So that must be what was differentiated. Now I'm going to differentiate it in my head using the chain rule. So derivative of e to the 1 minus a half x is e to the 1 minus half x. Cool. But then I'd have to multiply by minus a half because of the chain rule. And I don't want a minus a half there. So I'm going to put a minus 2 to cancel the minus a half. And also there's a 4, which I do want. I do want the 4. So I'll put that there as well. So overall, the answer is minus 8 e to the 1 minus a half x plus c. Now, the third one, oh my goodness, it's really hard without that little squared on, because the derivative of the bottom on the top is this. It's one to keep an eye out for. All these 4 are ones to keep an eye out for. And if I've got a fraction and if I differentiate the bottom and I see it on the top, I know the answer's learned, the end. So what's the derivative of x cubed plus 1? It's 3x squared. As this stands, we can't write learn because the derivative of the bottom isn't on the top. We can't use division because the bottom isn't linear. We can't use partial fractions because the bottom doesn't factorize. We have nothing, okay? We have nothing at all. And it's because I forgot to put that squared on. Now it's gone from being impossible to being easy. Now it's easy. The answer is learn x cubed plus 1. Now we think it through. Derivative of learn x cubed plus 1 is 1 over x cubed plus 1, and then you multiply by 3x squared, don't want the 3, done. Couldn't we use a substitution? It's not obvious to me how we could use a substitution on this one. X over x cubed plus 1, no. I don't see what substitution, I mean, what could we do? U is x cubed plus 1. So du, but it's not going to work. Look, du by dx is 3x squared. Dx by du. So this would equal x over u, and then we'd have 1 over 3x squared. That squared would cancel that, but then I'd still need to write x. So it would be 1 over 3u and then x, which is u minus 1 cube rooted. Yeah, see, it doesn't work unless, it only works, the learn, if the derivative of the bottom is on the top like this. So look at this. When you differentiate this, what do you get? Learn says that we get 1 over. So we get 1 over x cubed plus 1. That's that bit. Then you multiply by the derivative of the inside. That's the chain rule, the derivative of the inside. So we'd have to multiply by 3x squared. So if that squared isn't there, then this is wrong. Okay. With the denominator needs to be linear if you're doing division, because you only need to divide by a linear factor. So if the bottom isn't linear, it's not division. Right, I don't think there is, I can't think of a substitution that's going to work there, I'm afraid. I can't think of one. I think that one without the x, I think is pretty impossible. Without the squared. And with the squared, it's easy. Okay, now I'll talk you through my little sneaky method that I did here. You can use division. You can do x add 1 over x add 2. You can do it as division, just dividing by the x plus 2. So the way that that would look, if you did it with synthetic division, it would be 1x squared and one number, 1 and 1, divided by the thing that makes it 0 is minus 2. You'd put a 1 there, and then you'd multiply these together. Minus 2 and 1 is minus 2, and then you add them up and you get minus 1. And that little lovely little tight little box there, you don't need partial fractions. Partial fractions is when the bottom is factorized or factorizable. That's when you need partial fractions. This one is algebra, just basic algebra. So that guy can be written 1 minus 1 over x plus 2. And there are two ways to find that out. One of them is like I did down here with the synthetic division, that really cute little nice tight little thing. This one here is that 1 there, and that minus 1 there is that minus 1 there. It's really lovely. But the way that I showed you while you were still doing it quietly is this. So instead of writing x add 1, I'm going to write x add 2. And the reason I've written x add 2 is because I want x add 2 because it's x add 2 on the bottom. Oh, you're talking about, yeah, again, partial fractions. You have to have a factorizable bottom, and that isn't a factorizable bottom. Even after the substitution that I did, it was even worse. It wasn't a factorizable bottom. So partial fractions is no good there. You can't factorize that. That doesn't factorize. That's the problem. It would if it was a minus, but it isn't. It's a plus. So the little trick that I did was I wrote it as, instead of x add 1, I've written it as x add 2 minus 1, which is the same thing. That then allows me to think of it in this V shape, x add 2 over x add 2, and then 1 over x add 2. And then that allows me to just write down the answer straight away, which is x minus ln x add 2 plus c. Oh, hang on. So you're saying that this does factorize x. Oh, of course it does. Minus 1 is a root. X add 1. Yep. Yeah, I agree. Minus x add 1. Okay. X on the top. So, all right, this is a minor diversion because we're meant to be talking about parametrics, but say we take this x over x cubed plus 1. And we write it as x over x plus 1, x squared minus x plus 1. Now, partial fractions is where you unadd things. You unadd them. So you say this was actually originally two fractions with different denominators, and they got added up, and that's why the denominators were made the same. So the partial fractions is unadding. This direction here is partial fractions, and this direction here is adding, adding fractions. It's unadding. Okay, now, if I put an A on there and a B on there, now what I'm saying is that if I add these up, then I will get the x over, okay? If I add these up, I will get that. Now you could go ahead now and you could go blah, 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 and then add them up and then get some equations and da, 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 da. But just literally, just by looking at this, can you see that A has to be 0? At the moment, the way it stands, the way I've written it, A has to be 0. And the reason is because when you multiply top and bottom of this by that, then this is going to have an ax squared. And there is no ax squared there. There's no x squareds on the top. So if I have a number over this and then a number over this, and I try to add them up, it will never, ever look like that. Never. It will never just be some x's. It will definitely have some x squareds on the top of it. So it doesn't work. Now, what about if I did this? No, not that's making it worse. What if I did this? I don't know, I did a D. What's wrong with the C? Now I've dealt with that problem, right? I have dealt with the problem because now when I add them up on the top, I will get this. And then I will get bx plus c multiplied by x plus 1. And I want that to equal x. Now I can force that to have no x squared bits because I could make this x squared bit and that x squared bit, I could make them equal 0. So long as I have a is minus b, then it might work, okay? But yeah, it's a really difficult one. The partial fractions are really difficult structure. You'd have to set them up very carefully. Then you'd have to find all the things. And then even at the end of the day, don't forget, right back to what I was saying at the beginning about integration, that all the things do, like parts, substitution, fiddling around with fractions, fiddling around with trig, expanding brackets, la, 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 la. All those things do is bring you back to the situation here, okay? That's all that they do. And what you were talking about doing there, it wouldn't get us back to the thing. We could do that one, that would be learn, but then we couldn't do this one. So it wouldn't actually help. Right, that is your integration for today. Now we're going, oh, I didn't write any questions down. Well done, me. I'm going to go to my lovely, actually, sod it, we can make one up, okay? We can make one up. You tell me, I'm going to show you how to convert any parametric function into Cartesian. So I want you to tell me what x is and tell me what y is. So you can do trig or not trig. You can't do a combination, okay? So either has to be that they're both trig or they're both not trig. But you can have any function you like for x and any function you like for y, and the angle can be 2t or t or whatever you want. I want, no, because Ruhab, it's parametric functions are where both of these ones are described in terms of t. So x is something to do with t and y is something to do with t. Right, x is 2 cos t. What should we have for y? So we need a y to be a trig one now because we're doing trig, but it doesn't have to be cos. It could be sine or cos or tan or sec or cosec or cot, and it could be 2t or t, the angle. Literally anything. So Riyadh, we want a triggy thing. So it's either going to be trig or not trig. Y is 2 sine t or sine 2t. I'll tell you what, we'll do 2 sine t first, and then we'll do the same thing, but we'll do sine 2t to see the difference. Okay? Oh, I prefer 3 sec t minus 10. Can I do that one instead? That's way more fun. Okay, right, number one, job number one, do the angles match? Yes, they do. T, T. Here, no, they don't. So we'll have an extra job to do there, but here they match, so that's fine. So this is what you do. You write down your lovely hexagon, and the hexagon consists of tan, sine, cos, and then opposite is the reciprocal. So the reciprocal of tan is cot, the reciprocal of cos is sec, and the reciprocal of sine is cosec, and there's a 1 in the middle. And the 3 Pythagorean identities that you learn are sine squared plus cos squared is 1, 1 plus cot squared is cosec squared, and tan squared plus 1 is sec squared. So it's encapsulating your 3 Pythagorean identities. Now what you do is you circle the functions that you've got in your parametrics and their reciprocals. So any trig function mentioned at all, put a circle around it, but also put a circle around the one opposite. So in this case, I've got cos, and then opposite cos is sec. And then I look at this one and I'm like, oh, sec. Okay, I've already done that one. So the opposite is cos. Okay. So usually what happens, and it would have happened if I had sine. Look what happens if it's sine. I'll do it in green to differentiate. If we'd stuck with y is 2 sine t, then when we did our hexagon, tan, sine, cos, cot, cosec, sec, 1, then I would have had cos and its opposite, and I would have had sine and its opposite. And then you can see that only one of the 3 equations is going to work, because I'm looking for which ones are circled. So sine squared plus cos squared is 1, that would work. 1 plus cot squared is cosec squared, wouldn't work, I haven't got cot. Tan squared plus 1 is sec squared, wouldn't work, I haven't got tan. So the green example shows you what almost always happens, that you get 2 and then you write down the one you want. Sine squared t plus cos squared t is 1. Now in the blue situation, I've only circled 2. Now this might seem like, well, which one am I going to write down? What it shows you is that you didn't need a trig identity at all. It's actually easier than you even think, because sec and cos are just the reciprocals of each other, aren't they? And we're trying to do simultaneous equations here. We're trying to get rid of the t. So if it was not trig, if it was like a quadratic and a linear or something like that, it would literally just be simultaneous equations. Get rid of the t, rearrange one, put it in the other one. And in this case, we can just rearrange one and put it in the other one. So look, well, do you want me to take, and I'll take the first answer here. So put your fingers ready on X and Y. Do you want me to get X and rearrange it, or do you want me to take Y and rearrange it? Let's see how long the lag is now. X or Y? X, right. X equals 2 cos t. X over 2 equals cos t. 2 over X equals sec t. Done. Sub it in, rearrange, put it in the other one. Y equals 3 sec t minus 10. Done. A Cartesian equation is one without any t's in. That's got no t's in. Done. I'll show you what happens with the green one. It's always the same. It's always the same steps. It always works. So with the green one, we circle cos and then we circle sec because it's opposite cos. We circle sine because we've got sine, and then we circle cosec because it's opposite. And then we choose this equation and we're going to sub into it. Ibrahim, I have many tricks. So let's have a look. X is 2 cos t. So x over 2 is cos t. So x over 2 squared is cos squared t. That's what's going to go there. Okay. Now y. Y is 3 sec t minus 10. So y plus 10 all over 3 is cos t. So y 3 over y plus 10. No, other way around. That's sec. This is cos. Sorry, there's not much room. It's because I was only intending to do 2. Okay. So 3 over y plus 10 squared is cos squared. Oh, that goes in there as well. But look, I'm done. Cos squared t is x over 2 all squared. Cos squared t is 3 over y plus 10 squared. So therefore, these must be the exact same. X over 2 squared is 3 over y plus 10 squared. Or even that. Make up another one because I want to show you that this always works. So make up another, I'll get rid of this, and I want you to, and then we'll come back to the one with the different angles, but I want to show you that this process of using, I'll leave my hexagon there. So x equals y equals, do some sort of tricky one. X equals and y equals. Like make it as hard as you can. Use like whatever you think the hardest trig is out of sine, cos, tan, sec, cosec, cot. Literally anything. X is cot 2t. Okay. Oh, Ruhab, that is a really good one. 4 tan and 5 cos. That's a really difficult one because it's not just, you wouldn't get one like that basically. It's much, much, much harder to force them into each other. So you'd only have one. Annabelle said, oh, I like this one. X, oh, let's do this one as y then. 3 plus 2 sine 2t, like that. It would only have one trig function in each for you to be able to do it. Okay, it's good. So really nice thing here, and this is really important, is that the angles match. Now the angles are both 2t, but that doesn't matter. So what you'll find in this situation is loads and loads of students changing this to 2 sine t cos t, and then trying to change this to like tan 2t is 2 tan t over 1 minus tan squared t, but upside down because it's cot, and then getting in a big mess. It's absolutely fine. If the angles match, we're very happy. The angle is just the angle. It really doesn't matter. So we move on from here to our hexagon. Circle the functions and their reciprocals. So we circle cot and its reciprocal, and we circle sine and its reciprocal. Now we can see that the one that works is 1 plus cot squared is cosec squared. 1 plus cot squared 2t is cosec squared 2t. There's the angle that I didn't mind that was 2t. And now I'm going to sub into it. So I'm going to take the x. If x is cot 2, oh, well, that's easy. X is cot 2t. So x squared is cot squared 2t. So that's x squared. That's that bit done. Easy peasy. What about this one? Y is 3 plus 2 sine 2t. I need to make that say cot or cosec. Right, y minus 3 divided by 2 is sine 2t. So 2 divided by y minus 3 is cosec 2t. Done, squared, squared, finished. Okay, always, always works. The examples that you've just seen, that one, and the, oh, where's it gone? Where's the one that we did at the beginning with the 2? It's gone. Oh well, the ones that we went through, and then these ones, that it shows you hopefully that it always works. Now, if they're not trig, then fair enough, you have to do some fiddling around. Okay, and if they don't match, then you need to make it fiddle around. Oh, I did deleted it. Yeah, Abraham has one. Okay. So I'll do it again. I'll delete it again. And then hopefully I won't forget this time that I've done it. X equals a half cos 2t. Oh, this one's lovely. Y equals sine t plus pi by 6. Right. Now, this is a situation where this is no good. Our angles don't match. So we have to use our double half angle and our addition formulae to make them match. Okay, so y, I'm going to just rewrite it. X is a half, I'll probably go with 2 cos squared x minus 1, cos squared t minus 1. I'll probably do that one. Could have done 1 minus 2 sine squared. And y is sine t sine pi by 6 plus cos t cos pi by 6. Yeah. How do you remember which way around to write the hexagon? I remember it as tan is sine over cos. And then once you've got those 3 on, then the opposites are just the, oh, not cos squared. Oh, yeah, no, it is cos squared, isn't it? Cos 2t, cos 2a is 2 cos squared a minus 1. Or you could use cos 2a is cos squared a minus sine squared a. Or you could use cos 2a as 1 minus 2 sine squared. I went with that first of all, but I'm going to just see what happens. What am I going to do? This is not, I might have to move on from this one, Ibrahim, because it creates a situation that you wouldn't get where you've got two of them. I'm trying to think if I can make it. I've got cos, which means I can have sec. That's no problem. The cos is not a problem. I think I can do this. Did you make this one up? So what I could do is I could make the first one, the x, say cos t equals, and then sub that in, and that would mean I've got no more things, but I don't think, yeah, you didn't make it up. Where did you get it from? And it's one that you have to convert it to Cartesian. Right, now you've challenged me. Now I want to do it. So that's cos squared t. You have to convert it. Well, the most obvious thing for me, because we've got these two things, is that I am going to, oh, I know what I can do. Yeah, it's fine. Yeah, it's fine. Yeah, okay. So, so what have we got? We've got cos and sine, and that's it, cos and sine. So we've got cos and its opposite and sine and its opposite. So the only one that's got both of them is that one. So I'm going to be using sine squared plus cos squared is 1. Okay, x is cos squared t minus a half. So that one's pretty easy. Cos x plus a half is cos squared t. So that goes there. So that is x plus a half. So that was easy. Now I have to deal with this thing here, right? Y equals 1/2 sine t plus root 3 over 2. But right, I do actually know what cos t is because it's the square root of this. So I can sub that in. And now I can make it say sine t equals. It's disgusting, but y minus root 3 over 2 root x plus a half times 2 is sine t. So if I square both sides, then I can put that here. Done. I'm sure I can do it in a much nicer way than that. I'll think of the nicest way I can do it, but that does it. That's one way of doing it. But the difficulty here, the difficulty was that you have more than one trig function in there. If you only have one trig function in there, it's easy peasy. Okay, what do you need to be able to do for, yeah, it's disgusting. It's really disgusting. Like the ones that I was showing you before are much nicer. So what do we need to be able to do with parametrics? We need to be able to convert to Cartesian, which is either simultaneous equations or you can use that method I just showed you. And the next thing is differentiating, which we already talked about this week. It's the chain rule. And integrating, which I'm going to come on to, but it's just substitution. It's the exact same as the substitution I showed you yesterday. So actually, there's nothing new. Okay, this is the chain rule. Really, really easy. We can have any function we like. Let's scroll back and find some of the x's and y's you said earlier. Annabelle had 6 cot 3t, and then Raseb had sine 2t plus cos t. Okay, so what is dy by dx? dy by dx is the derivative of the y derivative of cos is not cos. There's the derivative of the y divided by the derivative of the x. Derivative of cot is a minus cos x squared. And then the chain rule says multiply by 3. Done. Done, that's it. You might be asked to find the equation of the tangent. Now, if you're asked to find the equation of the tangent, then you are basically needing to find three things. You need to find the gradient, you need to find the x coordinate of a point where you're taking the tangent, and you need to find the y coordinate. That's your jobs. Same thing with the normal. If you're finding the normal to a parametric equation, then you do still need to find the gradient of the tangent, but you're then going to flip it. So it would be this thing negative and upside down. So how do I get those three things? I get them here and here and here. Three things, right? So sub your t in there to get the x coordinate. Tick. Sub your t in here to get the y coordinate. And sub your t in here to get the gradient. Done. Chain rule, literally that's all there is to it. Converting parametrics, differentiating parametrics, integrating parametrics. So differentiating parametrics, really, really straightforward, really lovely, really simple. The derivative of the y on the top, the derivative of the x on the bottom, done. Integrating, bit more tricky, but it's just substitution. So if you remember that it's just integration by substitution, then you can use those methods that I was showing you yesterday. So how does that work? Well, normally we would write down for that area, we would write down the integral from a to b of f of x dx. That's what we'd normally write down. And then f of x would be a function to do with x, and then we would integrate and we would sub in the top limit and we would sub in the bottom limit. Okay. Now, in this case, we don't want to be working with x's, we want to be working with t's. So job number one is that we're going to change the a to what t is. So what we'd have to do, I'm going to go back and grab two more random functions here. X equals 1/2 cos, oh, we can use your ones that I couldn't convert. Y equals sine t plus pi by 6. We could use those. I mean, obviously, I hope you realize that that picture is not this function, but it doesn't matter. I'm just using it as an example. So what can we do? Let's say that the bottom limit is, for the sake of argument, this is a 1 and this is a 6. Then we'd say, right, when x is 1, what is t? This is what happens, Ronnie, when you think you made up the examples before you made the lesson, and then you forgot to actually make up the lessons, and then the numbers don't work. So x is now 0, because I just tried to solve that and realized it didn't solve. X is 0. What is t? Okay, 0 is 1/2 cos 2t. So cos 2t must be 0. So 2t must be pi by 2. So t must be pi by 4. So we change the t at the bottom. I'm finding the area under the curve and doing the integration. So what do we do when we're doing substitution? We change the limits, okay? We change the limits. That's what we do at the beginning with substitution. We change the limits. It's the exact same thing. So I change the bottom limit and I change the top limit. So that can't be 6 anymore, but this is just a demonstration of how you do it. So you'd say x equals whatever the top limit is, and then you'd say, what is t? And then you'd have, like, say you had a third is cos 2, 1/2 cos 2t. Right, I'm changing it to a third. Oh, it let me do it. That's a third. How did I get pi by 2? Just out of my brain. When is cos 0? At pi by 2. So then we would get 2/3 equals cos t. So t equals whatever. And that would be the top limit. So this is the limit changing thing, which is exactly what we do in integration by substitution. Now, what's the next thing we do in integration by substitution? I always say with integration by substitution, start by going by dt dt or by du du. And then sub in. It's exact, that's the end, right? Sub in. I'm going to literally sub in So instead of this at the bottom, this is going to be pi by 4. And at the top, it's going to be whatever the inverse cosine of 2/3 is. That goes at the top. And then see here where it says f of x. Well, y is f of x. F of x is y, yeah? Y and f of x are just different notations for the same thing. And I know what y is. Y is this. Now dx by dt. Well, I know what that is. X is a half cos 2t. So dx by dt is sine 2t negative. That goes here. And then off you go, you do integration, blah, blah, blah. So, chain rule, if you think of the chain rule not as being, just as being and then multiplied by the derivative of the inside, then hopefully you can see that parametric differentiation is just the chain rule. Integration by substitution, if you do it the way that I suggested with the changing it to by du, then shoving everything in, then it's literally the exact same. You don't have to learn any new method. It's exactly the same. Right. Yes, we can do an example. I can't make up a parametric integration because it has to all work, but I'll find one in this book. This is a lovely book, by the way. This is like the most famous A-level maths learning book, Bostock and Chandler. It still is. It's the Bible of A-level maths, Bostock and Chandler. Parametric equations, parametric differentiation. It's probably in there. I'm really sorry I didn't make up ones before. I thought I had done it. I thought I'd put the questions on. Yeah, I think it might be in further maths. Let me grab, how long have we got? We've got 4.5 minutes. I'm going to grab a book and then I'll write one for you. Okay. I am now using CGP A-level, full A-level. Okay. Okay. So let's pick one that looks hard. No, it's not that hard. Let's just do this one. The curve shown has x equals 4t, t plus 1, y is 3t cubed. It looks like this. And this is 8, and this is 120. And we want to find that area. Okay, so the difficulty or the not difficulty with parametric integration is to do with the integral that you end up with. The actual process is just substitution. So let's write down what we would write down initially. We'd write down this. The bottom limit is 8. The top limit is 120. Whatever y equals, that's what we'd write there. And then we'd write dx. So that's a normal way of finding the area under that curve. So what I'm suggesting we do is do integration by substitution. What is integration by substitution? We start off by changing this to by dt dt or by du du. And then we sub in this and we sub in this and we change the limits. Normal integration by substitution. So the y function is 3t cubed. The dx by dt function, oh, annoying. I'll have to expand it out. That's that bit done. Now I need to change the limits. So when x is 8, then 4t, t plus 1 is 8. So t squared plus t minus 2 is 0. So t is t plus 2t minus 1 is 0. T is 1. It says in the question that t is positive. So when x is 8, t is 1. So the bottom is going to change to a 1. When x is 120, I don't know what the answer to this is. Does anyone have their calculator handy that just does this? 15 and 2, 3 and 10, 5 and 15 and 2, 3 and 10, 5 and 6. Done. Yes, thank you, Prim. Thank you. 5 and minus 6. And it says in the question that t is positive. So what happens when we do integration by substitution, notice that this is not a version of integration by substitution. It literally is integration by substitution. Literally the exact same, but not if, not if you introduce the u for the substitution. If you think of it as by du, and then think of it as subbing in dx by du, or in this case dx by dt, then it's the exact same. So in this case, it would turn into 1 to 5, 3t cubed multiplied by 8t plus 4 dt. And then you'd expand it out and you do all your normal stuff. Okay. Apologies for the 2 things that went wrong today. One of them was that I got kicked off my year 12 stream and had to use the same stream for both. And the other apology is that I didn't put questions already on here ready to go. I thought I had done that. I don't know why, unless I did it and then just deleted it or something. But I hope that I've given you a good summary of what you need to know for parametrics. And also we did a little bit more integration that we'll do every single day. Okay, inside your exam units, we now have 2 days off, hooray. So we are going to be just chilling for 2 days. I suggest that you don't do any more maths unless you want to. I'll make all of these things available for free over the next, well, it won't even be 24 hours, it'll be the whole weekend. So you can make sure that you are up to date on the integration, on all of the parametric stuff and all of the vector stuff this weekend if you want to. Grace, I'm going to be doing other work this weekend. God forbid I take a day off. No, but Grace will be inside the Tailored Tutors course and she will be helping you out answering your questions. And next week, in terms of these 1 o'clock lessons, we'll be doing stats and mechanics overview. So normal distribution, hypothesis testing, moments and friction, which are the most important bits of the applied part of the spec, okay? It's in your schedule. Normal distribution, hypothesis testing, moments in mechanics, and friction in mechanics. I'll see you at 4 if you want to do an hour of study. Then I'll be doing 4 till 5. Otherwise, I will see you on Monday. Have a lovely weekend stuck inside.